All right, so you might know me better as Style Warning. I post hot takes on the internet sometimes. Before I get into the main matter, I want to give a little bit of context. So I've been using Common Lisp more or less exclusively professionally for the past 15 years. I typically maybe don't write as much Common Lisp as I should because I'm managing a team, usually between 5 and 20 people, plus or minus. The teams have a mixture of novices and experts. I don't just hire teams of people who only know or are experts in Common Lisp. They may have very little experience with Common Lisp. And if anybody's applied to a job that I've posted, say, over the past 5 years, may know about many of the restrictions. You have to be eligible for a clearance. You have to move to the United States. You have to be interested in quantum computing. You have to know a minimum of linear algebra, calculus, all this stuff. And so similar to the previous talk, sometimes there are issues finding a Common Lisp programmer who fits all of those criteria. So like others have said previously, I also need to hire people and train them frequently. So first key point is maintainability, reviewability of code, ease of onboarding onto software are very important to me in order to do my job. Second bit of context I want to share are the types of projects that I've worked on, professionally specifically. Firm real-time autonomous control, so by firm here I mean it's not quite soft real-time, but it's also not quite hard real-time. You can miss some temporal deadlines and things won't go terribly, but you can't miss too many or things will go terribly. I've talked a lot about quantum computer simulators and compilers in previous talks online and so on. A quantum computer simulator, for example, may use terabytes of memory. Numerical efficiency is very important in those circumstances. Mission critical systems, mission critical, quote unquote. What I mean by mission critical here is a failure in the software means one of two things, either a grave financial issue, losing lots of money, or lost lives. People could die if software doesn't work. Processor emulators, high-speed computation, all of these are sort of in the domain of things that I have worked on or currently work on. So performance is something that is also very, very important to me. This is the only ad I'll give, but I am hiring. I'm not hiring for quantum computing. I left quantum computing at the end of last year. I do love quantum computing, but I decided to move on after 10 years of it. I'm in a different domain now of this firm real-time control with signal processing. There's a lot of programming, math, physics, typical stuff. It is 100% Common Lisp in Coalton. It's not that there's a little tiny bit of Common Lisp around this giant shell of Python or something like that. I am hiring, but I am prioritizing resumes of people who would like to live in the Cambridge area and Massachusetts. So I'll put my email up again at the end, but if you're interested, let me know. Coalton. I'm going to speak a lot about Coalton. As a show of hands, who here has used a language like StandardML, OCaml, Haskell, maybe Rust, or languages very similar to that? Okay, so a good number. I don't like to discuss languages by just launching into like features, and this is not a talk to proselytize Coalton for what it's worth. I want to just skip and show an example right away. So I don't know if you can see my mouse. I'm going to try to use my mouse instead of a pointer for the folks online. This first bit of code here is adding a new data type to Coalton that mirrors an existing Common Lisp data type, namely a keyword. A Common Lisp keyword is the data representation of a Coalton symbol here. We have a way to make one of these symbols with this little constructor function, sim, which will just take a string, turn it into a keyword using the Common Lisp intern function. We allow symbol to participate in the EQ type class. This is the same EQ type class from Haskell. This is saying that in order to compare symbols for equality, we need to check if they're EQ. So this first bit of code is almost like binding code. This is a way to import something from Common Lisp into Coalton. The second is an algebraic data type. This is a very simple algebraic data type parameterized on a type variable t for mathematical expressions. So we can have constants of this type variable t, we can have variables, and we can do addition and multiplication of two expressions. Each of these lines here is a constructor, so we can construct an expression 4 different ways. In Common Lisp, you might either use a superclass and maybe 4 subclasses. You might define different structs. You might do the really old school Lisp way and just use symbols and lists. And then finally, on the right here, we have the typical differentiation program. We do a pattern match on our input f. If it's a constant, the derivative of a constant would be 0. If it's a symbol, either that symbol is equal to what we're deriving against, which would be 1 or 0, etc. It's the bog standard SICP definition of a differentiator. And then finally, maybe a little bit more interestingly than some of these previous things, is we have 2 things here. One, we can define t as the symbol t. So in Coalton, we're not automatically using the Common Lisp package, which means we can finally use the variable t. And second, we can define a differentiation operator, which is this diff function applied to just a single argument. So people familiar with Haskell, this will be very familiar in that the functions by default are curried. So we can partially apply one argument. The result of this will be a function of an expression to an expression. So I just wanted to give a look at what Coalton is before diving into all the features, kind of give a feel for just what it looks like. Getting started with it is very easy, at least if you're a Common Lisper. If you're not a Common Lisper and you don't know Emacs or how to install SBCL or whatever, okay, maybe it's a little bit more difficult. But if you know all of that, you just download Coalton from GitHub, you just quick load it, and that's all there is to it. There's no separate tool chain, there's no separate compiler programs, there's nothing else. It's just Lisp code that you load. You can use it in the REPL. You can switch to Coalton user to start running Coalton expressions right away, or you can start a new program. The main thing I want to point out with this program is instead of using the Common Lisp package, we use Coalton, and perhaps, if you prefer, Coalton Prelude. Coalton, as a project, uses a lot of package local nicknames. This is perhaps unusual to some Common Lispers, but for the organization of large programs with lots and lots of distinct modules, package local nicknames are extraordinary. They make things really easy. So a lot of Coalton programs will also have typically a big list of nicknames for all the standard library packages that you want to use. And then down here, you write your Coalton code in Coalton top level. Then everything I showed on the previous slide, you can just write in there. Again, this is a .lisp file. You put it in your normal .asd file. It's in the normal compilation chain and everything. Coalton is really just a Lisp macro. At the end of the day, it's an extraordinarily sophisticated Lisp macro that takes probably 100 different files to author, but at the end of the day, it really is just a Lisp macro. A little bit about Coalton. It started in 2018. Actually, the first time I talked about Coalton was at SBCL 20, where I kind of shared this idea like, maybe we should have strong types in Lisp. Coalton is open source. It's MIT licensed. Statically typed. The type system exceeds that of Haskell 95. So it has multi-parameter type classes. It has a Hindley-Milner-based type system. It has other extensions, again, that aren't present in typical Haskell. All these things are in GHC, for those familiar, but not in the standardized Haskell language. It is functional, but it is impure. So you can do I/O. You don't have to thread everything through monads. That may be a great benefit to you, or you may hate that if you're a strictly, strongly, statically typed, functional type programmer. Given that this is a Lisp conference, I assume people like to just print stuff by calling print. You can do the same thing in Coalton. It's strictly evaluated, so you don't have to learn laziness or anything like Lisp, Scheme, OCaml, Rust, etc. It's a Lisp 1. Even though we're writing Coalton code within Lisp files, the language of Coalton itself is a Lisp 1. All global variables are lexically scoped, so you can shadow things. If you write a lot of Scheme, Coalton will feel very natural. It is optimized, so Coalton is more than just a typed language. It has a lot of optimization built into it, which we'll discuss later, and it's real world. This has been used for about the past 5 or so years, 5.5 years, first in quantum computing and now serious defense applications. It is fully compatible and interoperable with Common Lisp. You can call Lisp code from Coalton, Coalton code from Lisp. It's a Lisp macro, so it's all turned into Lisp anyway. There's really no impedance mismatch between it, at least in my opinion. Like I said, Coalton is actually used. You can find some big swaths of open source Coalton code if you want. It's going to be kind of nutty quantum-y stuff. But there is a discrete quantum compilation routine that's implemented that takes one of these state-of-the-art papers, It has a bunch of number theory and stuff. It's a lot of math. Same with this global quantum optimizer. This was actually a capstone project for a master's program from UCLA for an intern that I had, and they wrote their entire thing. They actually didn't know Common Lisp either. They actually started with Coalton, wrote this amazing software package for doing global optimization of quantum circuits and implemented in Coalton. There's an implementation of the Haskell type checker, not Coalton's type checker, but a separate implementation of a type checker for Haskell written in Coalton, and then all the Coalton standard libraries in Coalton. From a proprietary standpoint, there's a lot of quantum applications. I won't talk about many of them because they're proprietary. A particular, very involved signal processing application, and even a protocol buffers generator for the real, corporate vibe, I guess. Most Coalton code that exists are actually just protocol buffer bindings, by the way, which is kind of sad. But I'm not going to go through this comprehensively. I'm going to point out a few things, but this is roughly what Coalton is as a language. It has several different top-level operators. You can define variables and functions. You can define structs. You can define new types, specifically algebraic data types, parameterized on type variables. You can define type aliases. You can define classes. These are type classes, not Lisp classes. You can define instances of those type classes, meaning you can say a type participates in this type class. And then you can declare variables as having particular types. Expressions, I'm not going to go through all of these. These are basic things. The two that I do want to point out are match, so pattern matching with exhaustiveness checking, as you'd expect from a language like an ML or a Haskell. And then Lisp. Lisp is an operator that lets you just put whatever Lisp code you want. It's like inline assembly, but it's inline Lisp, basically. Soon, we're going to add another feature here to have type-safe conditions. It's going through kind of the design process and implementation process, but probably within, 2 months or so, that will be included as well. The standard library includes things that are very useful to functional programmers specifically, such as immutable sequences and maps based off of RRB trees and hash array map trees. There's arbitrary precision floats. I've wanted this in Common Lisp forever. I think at SBCL 20, I'm like, SBCL developers, please let me extend the numerical tower. There's no way they're going to do that, obviously. I'm interested in it, but in Coalton, because we can build our own numerical tower, we have that. We also have computable reals. We have hyperdual numbers, whatever those are, for computing partial derivatives. We actually don't have quaternions in the standard library yet, so, if you want to contribute something, we would gladly accept it. Iterators, slices, whatever, a bunch of standard data structures. Okay, I want to go on a little bit of a tangent and talk about safety in quantum programming, or not quantum, in programming language evangelism. So safety is a big thing, especially these days with Rust and Haskell and whatever. In my opinion, just my opinion, safety doesn't really sell. I'm not saying safety is not important. I just talked about mission-critical applications that could kill people potentially if things are wrong. Safety, of course, is important. I just don't find it to be a very compelling selling point. Rust has been at war, especially if you're on Twitter. I don't know, heaven forbid, perhaps you're not. But if you are, you constantly see bickering about, we're going to rewrite everything in Rust, and C is, full of CVEs and issues and whatever. They've been at war for 13 years. Haskell has been at war with everybody who's not a Haskeller for 35 years now, harping on specifically safety. One of the favorite lines that people like to repeat is make illegal states unrepresentable. They'll tell you that, and then they'll link you like 6 PhDs worth of dependent type theory and category theory and whatever. Not saying that stuff is useless, not at all. I myself am very interested in it myself. However, I don't think it's good at selling people. So in my opinion, when approaching discussing languages, especially something like Coalton, which has type safety as a headline feature, that can't be the only thing of importance. A few of my opinions. In my opinion, type systems, the extremely sophisticated ones, really haven't earned their keep in industry. So if you look at Haskell, perhaps with a bunch of extensions, it's not being broadly used. There's a lot of advanced theory out there, but it has not yet made its way into industry. Another issue with, I think, type systems is that if you increase the complexity of your type system, you actually make it more and more difficult for somebody to replicate your implementation. There is not a second GHC out there. There's like 30 Common Lisps, but like only one GHC. It would be very, very difficult, if not impossible, to make another GHC. Type safety is very important in some applications. I think that goes without saying. But I think types give you much more than safety. Documentation is a big one. Software longevity, making sure bit rot doesn't happen. Collaboration, especially within a workplace, and performance. So I don't think safety should be anything special. It should sort of be a standard expectation. What do we get besides safety with a type system? We get performance. That's a big one. That's one that's, like I told you, very important to me. Coalton isn't just an implementation of a Hindley-Milner type checker with type classes. It's also a code optimizer. It'll do data representation selection. It'll do some escape analysis and stack allocation. It's maybe not great at it, but it does some of it. It'll seal your data structures. It'll know that you're not going to extend it or redefine it anymore if you set the setting to do that, and it'll optimize accordingly. It eliminates all runtime type checks because it's proving at compile time your program is type safe. So all the type checks, even the sneaky ones that you didn't catch with your speed 3, safety 1, or safety 0 or whatever, will just get eliminated. For SBCL specifically, it actually emits the, I don't remember what it is, SBC type check 0 or something like that. It has a heuristic global inliner. It has method inlining and type monomorphization, and there's a lot more that's sort of being planned. Coalton, at the end of the day, has more freedom to optimize than Common Lisp does, for many reasons. Coalton, perhaps this is a negative feature to Lispers, but Coalton actually has a development and release mode. So if you're done with your program, which many times we are, I am done with my program, I have to ship it on something at some point, I'm not going to be hooking in a Lisp REPL on it or anything. I can say this is for release, and it will turn on every safe optimization it can. So I want to talk about performance for the rest of this, and I want to use an example in signal processing. My job right now has a lot of signal processing. It has to be very fast. The bedrock of signal processing, in my opinion, is the Fourier transform. And so what I'd like to use is a simple implementation of a Fourier transform as a case study for performance. I want to only talk about performance derived from a compiler. So I'm not going to talk about the ins and outs of decimation in Fourier transforms or splitting by 4 instead of 2 or prime number sized Fourier transforms. I'm not going to talk about any of that. I just want to talk about how we can achieve performance through the tools of our language and compiler as opposed to algorithmic things. The best Fourier transforms out there are ones that have a lot of microarchitectural tricks, algorithmic tricks, and of course a good compiler. This will be the only math slide, I think, but I do want to talk about what a Fourier transform is for folks who don't know. Fourier transform in its sort of simplest form allows us to take something that looks like a signal. You could think of it as a function over time. It could be a function of space, whatever, some squiggly line. That's this red bit on the left up here. And what it does, the Fourier transform finds what size sinusoids, specifically what size and frequency, would you have to mix together to reproduce that signal. So the output is the list of sinusoids and their relative amplitudes that you would need to combine in order to make the original signal. So the input is something called a time domain signal. Like I said, it could be an image, it could be radio, it could be whatever. And the output is something we say is in the frequency domain. A function whose input is frequency and output is the amount of that that you need to put in to reconstruct the original signal. There's the inverse Fourier transform. You can go in both directions. It's a unitary operation. This is the algorithm for computing Fourier transforms fast. The fast Fourier transform is probably the most important algorithm ever invented, in my opinion. It is used everywhere, more places than you think. The algorithm itself for a signal of length n runs in n log n time. And implementations of the Fourier transform, even with that algorithmic benefit that you get from the fast Fourier transform, usually have to be incredibly efficient. So I think it's a reasonable case study. So the first thing I want to do is just write a very straightforward Fourier transform, a typical in-place mutating Fourier transform of complex numbers on an array. So typically, by the way, these signals as input are usually complex numbers. The outputs are usually complex numbers, typically. So here's one in Common Lisp. It is not necessary to verify this code is correct. It may have bugs. I don't think it does, but it doesn't really matter in this case. It doesn't matter exactly what it's doing, but I do want to point out a few salient features here. There's 3 loops here. There's this outer loop that's kind of growing by 2, so that's running a logarithmic number of times. And then there's this inner loop here, which is running linearly, and it's going through and mixing stuff up. It's, the main meat of it here are these 2 setfs in the middle. And that's what it's doing. It's doing a bunch of complex arithmetic on arrays, basically, in a loop. There's a little side function here to compute a root of unity using the CIS function, which stands for cosine I sine. That's the same thing as doing e to the I theta. And then the actual FFT driver at the bottom here is take a vector or signal x, calculate its length, get a primitive root, and call the main meat of the FFT function. There's nothing crazy here. This code is written in a way that a Fortran programmer would love. It is just loops in arithmetic, nothing else. No crazy functional programming or anything like that. Coalton is mostly the same. Maybe a little hard to read up here, but I'll point out these main things. The first thing is Coalton's looping facilities right now are a little bit, they're a little bit thin. So we use something like a named let. We call it rec instead of let, but it is a named let. That's a convenient way to iterate through something. Sometimes we have to use special division operators. Because we're type safe, we have to be clear about what we're dividing and what the result is. And so we want the division of 2 integers here to result in an integer. So we use a separate function for that. We don't have setf or setf expanders. So we have just functions that mutate themselves. So we have this array set bang function. But otherwise, it's mostly the same. And then we have this like unwrap try into thing. We have to explicitly convert between data types because Coalton is type safe. But otherwise, it's basically one-to-one. A couple little tiny differences to shore it up in terms of type safety, but otherwise, it's mostly the same. The driver's the same, but we had to do a little bit of extra work. Pretty straightforward. Mostly the same thing. If you can read Scheme or like a weird hybrid between Scheme and Common Lisp, this is straightforward. Okay, so I wrote a little driver function, this FFT test function. I'm not going to show what that is. It's basically just calling this thing, and it calls the function. It creates a random array of 2 to the 20 double floats, complex double floats, and it runs the FFT on it, just to see how much time in memory. So in both cases, we run it, the first one here, CL1, stands for Common Lisp. Coal1 stands for the Coalton one. We run this FFT test here, and we see that the Common Lisp version runs in about 1.1 seconds for 2 to the 20, and the Coalton version runs in 1.13. This is not rigorously timing, so there might be a little bit of slew and a little bit of standard deviation in the results, but whatever. As a general, like, lick your finger in the air, smoke check, it's about the same time in memory for each of them. Both are unoptimized, both are generic in certain ways, so this is a good baseline. So Lisp code is usually slow. If anybody has had to optimize Lisp code, you know the first thing you're going to do is start adding type declarations to it. So what I want to do first is just add type declarations to all the functions at the top level. So in Lisp, this is easy. I'm going to elide all the code. I don't know how well this green shows up here on the projector screen, but basically we're declaiming the F type of everything. This first function here is a simple array of complex double floats with just one single rank 1. Takes another fixed num, and then complex double float for this root of unity, whatever. Straightforward stuff. Just write the types out for each of these. The Coalton one, same thing. We write the types. The type syntax is a little bit different. In my opinion, it's more readable because we have this little arrow notation, which is infix. We're not sort of, I love parentheses, but maybe this is a little too many parentheses. Here, it's much more straightforward. Yes, we can parse symbolic, expressions. So we can parse infix arrows if we want to. So this takes a Lisp array of complex double floats and a ufix, which is an unsigned fixed num, and a complex double float, and returns a Lisp array of complex double floats. Simple. Same thing. Same concept in both Lisp and Coalton. Now when we run it, however, Lisp gets twice as fast, as we expect. This is in SBCL specifically. Coalton, on the other hand, gets 10 times faster. We get down to 0.1 seconds, no bytes const. Lisp is still consing up 2 gigabytes in this case. So any Lisper knows, especially if we know Coalton is being compiled to Lisp because it's a macro, surely the Lisp must be able to get faster. Of course it must be able to. So what do? We're going to add even more types. We're going to use the. We're going to change our compiler declarations. We're going to do all that stuff to make stuff fast. Again, anybody who's optimized has gone through this exercise at least once in their life. So the Common Lisp code looks like this. The red is sort of the diff. That's where we add all the types. So we add the global type declaration. We're going to say that our loop iteration variable is a fixed num and it will always be. We're going to say this little variable on the inside is a complex double float and it will always be. Instead of binding this variable to 1, we're going to bind it to hash c paren 1.0.0, 0.0 do, you know, a complex number literal, because 1 and 1.0 do are not the same. Whatever, bunch of type declarations. Usual thing that you do. And usually it's not so bad. I mean, I'm making it seem like it's horrible, but if you have to do this once, it's not really a big deal. Now, when you do this, you better be damn sure, of course, that your variables are not exceeding the size of a fixed num. They probably won't, or you're not accidentally storing one thing that shouldn't be. SBCL is pretty good at proactively telling you if you're making a mistake. And if we do that, we recover the speed that Coalton got. 0.1 seconds, 0 bytes const, everything is good, we're all happy. Code might be a little uglier, but at least it's fast. SBCL did a great job here. Probably in SBCL we could get by with a few, we could eliminate a few of the type declarations because SBCL is pretty good at propagating types. But in general, you're not looking to minimize type declarations when you're trying to make code fast. You're just going to say, whatever, declare everything. Great, all done, right? But now you wrote your nice and fast FFT, and you want to do a couple things. You want to make it a quick Lisp library, because why not? You want to make it work on something more than just double floats. Yes, we wrote a double float FFT, but why not single floats? Why not fixed precision integers? Why not integers themselves? Why not let the user define their own FFT over their own special data type? Now we're kind of in trouble. This is another one of my opinions. In Common Lisp, typically, you have to face this dreaded Lisp triangle. On the 3 points of the triangle are fast, generic, and simple. Generally speaking, you can only choose 2 of those. Let's kind of look a little more in detail if we were to choose one of these approaches for packaging up our FFT library and shipping it. So suppose we want fast and simple. Well, that's kind of what we did. What we wrote is very fast and very simple. It's just, you know, loops and arithmetic with a lot of type declarations. That's good, it's simple. Maybe we could put it into a macro, why not? The code is a little ugly, it's straightforward, and it's very fast. A big con of it, though, is that the code can't be generic. We could maybe do like templating macros. Maybe you've seen a couple Lisp libraries where we define macros, and the arguments of the macros are the types that you want to fill in for the code, and then you know, especially if it's a macrolet or something like that. It's not a pretty way to write Lisp, in my opinion. We could go the fast generic route. I don't actually know how we would do this. Maybe macro wizardry. Some people, like there's this inline generic function thing, so maybe we define this all as CLOS things, and then we use this inline generic function fun callable thing, and somehow it'll all turn into type cases, and then SBCL will somehow eliminate the branches of the type cases for each type of interest. I don't know. To me, the fast and generic is a little bit theoretical, but you know, if it exists, there's many pros to it. Oftentimes, though, you're kind of pushing the boundaries of what Lisp, Common Lisp in kind of its native form is designed to do. And then the last option here, of course, is generic and simple. This is by far the most common and preferred approach in, let's say, open source Common Lisp programming. We can use CLOS. We can make an FFT protocol. It's very succinct and flexible. It's easy to document. The cons usually are sometimes there are going to be ugly hacks. I'll show you one in a second. Because it's not using basic Common Lisp functions, it can be slow. All these reasons. So usually the fast and simple, or the generic and simple one is usually not the fastest. So let's do this as a third attempt at writing this FFT. This time we'll go for the generic and simple approach. We'll just implement it now for single floats and double floats to kind of get a feel for what this interface is going to look like. And then we're going to try using this to see if we can define an integer Fourier transform. So here's the protocol that I propose. We have these 5 generic functions. The obvious ones, plus, minus, and times. We need arithmetic, of course. This root thing to have a primitive root of unity in whatever type we're doing. And then we need this one function. One, the job of one is to return the value of one in that type. That already poses a problem. How do I write a generic function to return a value based off type? I thought generic functions are supposed to dispatch on some type, but now we don't have a type to dispatch on because it's not a function of a variable. So what we're going to have to do in this hack is provide the type to the generic function. We're going to represent that type as a symbol. Now you may say, okay, Robert, come on now. Like plus and times, we should be able to just specialize a generic function on integer or on single float or whatever. Well, Common Lisp doesn't have complex single floats as a class, so we can't specialize on complex single floats in standard Common Lisp. We can specialize on complex, but not complex single float or complex double float. Like I said, root here, root and one, those two functions are polymorphic on their output type. You need to provide the input type to describe what output you're looking for. This shouldn't be too unfamiliar. We have functions like this in Common Lisp, like the concatenate function. We have concatenate string, blah. We're telling it what output type we want, regardless of the input types. Don't ask me how to extend this protocol also to work with generic sequences. So yes, I'm talking about simple arrays here, but now if you want to make it work on lists and whatever, and it's going to turn into a mess, in my opinion. Okay, so the code itself is a relatively simple change. We go through, I took out all the type stuff for a moment because the type stuff doesn't make sense anymore. We can't declare types because the type is being provided at runtime. And so we replace all those call sites. Wherever we're doing multiplication, we replace that with times. Wherever we're doing addition, we replace that with plus. Whenever we want the value of 1, we use the 1 function. Pretty straightforward. It doesn't look so bad, in my opinion. So here's the implementation of the protocol. This is optimized for a slide, obviously. It's very short and simple. Single floats and double floats, it's very, very straightforward. And then you finally have at the bottom the driver there, the FFT SF and the FFT DF, to actually call it. In this case, we can actually see explicitly that we're specializing on the symbol. Here I'm using SF. Maybe if you're fine with verbose code, you can write single dash float. But again, that doesn't fit on a slide very well, so take it for what it is. We do that for single floats and double floats, and it works. This might not work very well in a very real-world example. It definitely works for this small FFT example. I don't know how well this approach is going to scale, but it works. The Coalton, on the other hand, was already generic to begin with. We never specialize it to work on any particular number type. It already works on all types that satisfy the properties that you need for numbers. The only thing we needed to add to our protocol is this type class up here, which is primitive root. This type class says that if a type t, which is a variable here, if this generic type t should participate in this primitive root type class, you must tell me how to make a primitive root. The input here is a uffix, and the output is this type t. This is a very subtle point that I'm not sure I'll be able to communicate it very effectively, that we have a generic function here, but it's generic on its output type. So we have a statically typed language where we have a function which is polymorphic and generic on its output type, not its input type. We didn't need to change any code here. It all remains the same. We just added this little way to get a primitive root. Here's the implementation. So we say for a complex single float, in order to make a primitive root, we call the cosine isine function on math.pi. Pi, by the way, is also generic. Math.pi is not a double float. It's an abstract number, which can be a single float or double float, depending on what context dictates. If context says it should be a double float, then it'll choose the double float pi. If context says it should be a quaternion or something, it will be a quaternion, so long as there's an implementation of it for quaternions. Same thing with single floats, double floats, and then finally our driver functions. It's just calling FFT. The same FFT in both cases, we're just pinning different types at the top level through these declares here. So we're declaring FFT SF as taking complex single floats, but we just call the normal FFT function. It's already generic. We don't need to change anything. Okay, we run it, and we're back kind of to not being so fast. Well, Coalton is faster. Coalton is 20% faster than Lisp in this case. We didn't do much extra work or anything, and we don't have these god-awful symbols that we're passing to functions or anything, and we still netted some benefit. We're not winning any benchmark games with this code, of course, but it is faster. You get kind of generic, a little bit of speed and simplicity in these cases, and Coalton ekes out a little bit more performance. I said that I would want to run this and make this work on integer Fourier transforms. So something very interesting about Fourier transforms, if you're into the math of Fourier transforms, is that you can actually talk about Fourier transforms over things that aren't complex numbers. The idea that you have a primitive root, which means you have a value such that when you exponentiate it a certain number of times, you'll eventually get 1. If your number system has numbers of that property, and a few other little caveats, which I won't get into, you can make a Fourier transform out of it. Well, what's another number type that does this? Finite fields. So you can take integers modulo a prime, and there will always be a number in that set of integers such that when you exponentiate it, you'll get back to 1. And there are primitive roots. So we can make Fourier transforms out of finite field elements, which are integers. In this case, we're going to do this mod, what is it, 7 million? 7,340,033. So integers mod 7 million and change, we're going to make a Fourier transform out of. OK, well, the Lisp thing is already sort of set. We're going to choose the symbol FF here. Just do all the arithmetic, but do all the arithmetic mod 7 million. And we get the same thing. Now, well, we're going to have the same issues. Speed is going to be really bad. This FF thing is going to be a nightmare to document to your users. Like, hey, just pass the symbol FF, and you'll magically get this Fourier transform over integers mod 7 million. There's a ceiling on performance. There's really not a lot of options we have here in this framework to improve performance if we wanted it. We'd have to go back to one of our earlier things where we write out the function and write all the types inside and whatever if we want to kind of achieve that performance. In this case, there's a ceiling, and we're not going to really get much better than it. Here's an example of Coalton. We're going to define a new type called finite field that has a constructor f here. So you give me a uffix. I'm going to construct a finite field element out of it. I'm going to tell it how to compare for equality. That's just integer equality, no big deal. I'm going to tell Coalton how to treat this thing as a number, which in Coalton, it's similar to Haskell. You have to tell it how to add, subtract, multiply, and how you convert an arbitrary integer to this type. In this case, I'm just going to shell out to Lisp. I'm just inlining Lisp, the same code from the last slide, because maybe Coalton doesn't have these things. Coalton actually does have modulo arithmetic and stuff like that, but just for the sake of example here, I'm just going to call into Lisp. So we call into Lisp. We tell it how to compute a primitive root. It turns out that, what is this, 4,665,133. If you exponentiate that enough, you will get back to 1. Therefore, it's a primitive root. Therefore, I can make a Fourier transform out of it. And at the end, we call the same FFT function, the one that was already generic, the one that we already defined. We don't have to write new FFT code for this. OK, so I just wanted to show how you could do this with integers. So sort of the conclusion of this is, for these types of, at least for this example, we saw that with about the same work, Coalton could be faster, while being more generic, in my opinion, less cumbersome. And the difference here is it's completely type safe. It's all going to be validated at compile time. We also showed how we could express more exotic number types. I don't know if integers mod p is an exotic number type. Hyperdual numbers and stuff are definitely exotic for an existing numerical algorithm. So we already had a numerical algorithm. We wanted it for a new type, and we could make that happen. But I have another trick, something I didn't say yet. One of Coalton's superpowers is monomorphization. This is something that you cannot do in Lisp, but we can do very easily in Coalton. So what is monomorphization? Coalton has a lot of machinery for doing generic stuff, and that's why at the end of the day, the Coalton code was at like 1 second or something. It still has to do a bunch of stuff to make generic arithmetic work. It still has to pass around these so-called dictionaries, these V tables or whatever in C++ parlance. It still has to do something to make generic code work. We can eliminate all of that machinery through monomorphization. So what I have at the bottom here on the left is sort of a call graph. This FFTDF calls FFT, which calls root and also calls this FFT root function. And I wrote a sketch of what the types of each of these functions are. FFT-df takes an array of complex double floats and produces an array of complex double floats. That's calling the FFT function, which is generic. That's calling an array of arbitrary type t, actually numbers of number types t, and produces arrays of t. The FFT function is now calling also a generic function, this root function, which takes an integer and produces a t. And it's also calling this FFT root, which takes an array of t, integer, a t, an array of t. It produces an array of t. So even though the top level function up here, this FFT-df, is a concrete monomorphic type, meaning it has no generic aspects to it, no type variables, no nothing, it's still calling a bunch of functions in its call chain that are generic. What monomorphization does is say, hey, take all of those things with generic type variables and fill them in with the actual variables that are used. So in this case, if we monomorphized FFT-df, it would make a new function, FFT star, replaces that type variable t with complex double float. It'd make a new function, root star, replaces that t with complex double float. It'd make a new function, FFT root star, which replaces that type t with complex double floats. It takes the whole chain of functions that are called, copies it over, and fills in the type variables for you. Seems kind of complicated to do, though. In Coalton, though,
it's like templates in C++ where we're substituting everything?
I would not say it's like templates because I don't want to have any connection to C++. But with that said, the principle is similar. What did you say?
It's the way of the Rust and Julia again.
Yes, yes. Rust, I don't remember about Julia. I guess that just-in-time compiles and can make specialized versions, monomorphic versions. Rust, definitely. Rust does a lot of monomorphization as well. What did you say? The bloat is going to be however much you're monomorphizing. So if there's a person that I work with who loves monomorphizing. He writes all his code, and then in each function that he writes, he's like, well, I'm going to make this faster. Monomorphize, and he just monomorphizes it over and over. It actually doesn't, for the applications that we've worked on, even when you're as aggressive as that, it's not so bad. You can roughly, in mind, estimate what the code bloat is going to be because it's producing common Lisp code that you expect. And in fact, I don't have a demo of this, but in Coalton, you can say, don't actually compile this code, macro expand it. So you can look at exactly how it monomorphizes if you're interested in how much bloat it's introducing to your binary. So in this case, in order to monomorphize the FFT-df, we just write monomorphize above it. That's all we do. We write our type declaration, we're calling our generic function here, and when you write monomorphize, the Coalton compiler is going to do all the work of going in and substituting those type variables, recompiling the functions for those types, and so on. And so when you do this, now you have fully generic code. The code is written in the original way that you intended it to, and it's really fast. So you can still write your code in a generic way and not worry sort of too early about hyper-specializing things. You can write things as generic as you want and then decide later whether you need monomorphization. So in my view, Coalton sort of achieves this fast plus generic plus simple dictum. Now, it goes without saying there are many caveats to this. So for example, there's a lot of discussion we could have about separate compilation. What if the source code wasn't available and you wanted to do this monomorphization? Well, you can't monomorphize if you don't have the source code. It's not really in the Lisp ethos to do separate compilation, generally speaking. So for the applications that we care about, that's not a problem. The code bloat is another one. What are we trading here? We're trading speed for code size. You can run into issues there. And in general, it might not actually improve speed in certain limited circumstances if you're blowing out your iCache or something like that. There are many other little considerations to make. But in general, monomorphization can be seen as a tool that you can reach for, similar to in Common Lisp, how you can declare optimize. That's a tool you can reach for. Or the operator in Common Lisp, or simple arrays or whatever. It's another tool that you can have in your tool belt to achieve fast code. So I want to zoom out a little bit and talk about signal processing in the large very briefly. That FFTs are like one building block. An FFT is just one Lego block in a larger application for doing signal processing. So I want everybody to imagine all the Common Lisp stuff that I showed you want fast or generic or simple or whatever you want, but now you want to apply these principles to a larger code base. Like it might be nice and good that I showed you how to make a fast FFT in Common Lisp or a generic one or whatever, but now imagine this is just like one tiny module in a larger application. The amount of work that it takes to scale performance or perhaps safety or any of these things is actually quite difficult. I would claim that Coalton simplifies that a lot. So we have a very large signal processing application for the company that I work for. It was mega optimized, like that one of the first slides I showed you with all the type declarations. We really, really, really ripped through this and optimized it as much as we could. And then one day, requirements changed, as happens in corporate world. And now somebody, the unlucky person in our issue tracker who gets assigned to this, goes and opens the code and they're like, oh my gosh, now I have to figure out, now I have to back out all the type declarations, implement the algorithm correctly, put the type declarations in, make sure there's a benchmark there so it goes as fast as it did before and so on. So we decided this was going to be a case study. This is existing code already for converting to Coalton. I don't remember how many lines it is. It's something across maybe 10 or so files, maybe 10,000 lines of code, something like that. And we just did a line-for-line port. Like I said, Coalton doesn't have all the same operators as Common Lisp. There are little changes you have to make. But we did that, and immediately, this is from the optimized Common Lisp code, we were already 10% faster, and we consed about 50% less. And that's just for a line-for-line port. That's not trying to use any additional things. Yep?
So when you say line-for-line port, the resulting Coalton code, the source code size is about the same?
Yeah, source code size is more or less identical, within 5% or so. There might be a few extra lines because we have this named let or rec or something like that. Obviously, this is just n equals 1. I'm not claiming that if you all go take your Common Lisp code and rewrite it in Coalton, you're going to get these amazing performance benefits or whatever. But for this application, this is what we got. OK, so like I said, I don't want to proselytize Coalton so much, so I want to tell you what's not good about it, what's not done with it, and so on. The standard library was built as you'd expect when your goal isn't really to build a language, but your goal is to solve industry problems. So somebody one day is like, hey, you know what? We need a tree data structure. OK, yeah, go ahead. Make a PR. Let's add a tree data structure. You know what? I need these hyperdual numbers. Yeah, go ahead, make a PR, add it. So we accumulated. The modules are not bad, to be clear. It's it's reasonable quality code. But nobody took a step back and said, you know what? I will design the standard library, and it will be beautiful with the greatest type classes and hierarchies and whatever. So I think the standard library could use a good refresh. It is a great place to go if you're interested in kind of learning about Coalton, trying it. Just write something in the standard library, add something new, clean something up. Some type system features are missing. So I have a lot of consternation every time Coalton somehow makes it to Hacker News. The reason for it is because inevitably there's always one comment in there where somebody goes to the issue tracker, and I have a pinned issue in the Coalton issue tracker that says, the type system is unsound in the presence of mutation. So for folks who don't know, the Hindley-Milner type inference algorithm by default, as described originally, has a soundness issue if you include mutation. It's possible to create a program which will result in a type error if you abuse polymorphism and mutation. We didn't fix that. There are several approaches to fixing it. We want to fix it the right way, not do the Band-Aid fix. We just haven't done it because we're not doing mutation on polymorphic stuff. It doesn't come up in our day-to-day application. But of course, the Hacker News person is, well, how can I trust a language like this if, it purports to be type safe, but, actually it's not type safe because if you're mutating polymorphic code, there's a small percentage chance that your code is going to be, it's that sort of thing. So there are some type system things that we need to improve. Integration with the condition system, I said earlier that this is something that's in progress, so making a nice way to do normal pattern matching, integrate with the Common Lisp condition system. It's actually relatively straightforward, the plan we're doing. If anybody's thinking here algebraic effects or something, we're not going to go down this route of, I don't want to say crazy type system features, but features that, again, haven't made their way into industrial languages before. So the way that we're going to do conditions is roughly the way that we're going to do it in the way that's done in Common Lisp. We're going to have signaling conditions and restarts. It's just going to be type safe. Many more optimizations are planned. This is an area where there's just a never-ending amount of work to do, but it's very fun to write optimizations for Coalton because, one, it's really nice when your target language is Common Lisp. Like, we're not generating assembly. Common Lisp is a much better language to generate than assembly or SBCL VOPs or, I don't know, IR1 or whatever it's called in SBCL. It's like it's just very straightforward. But now you also have all the types available. So now you can ask yourself, well, what optimizations can I do with types? And there are all sorts of ones, like ones that we want to do where we maybe elide, we want to make certain calling conventions for different functions. So if you're returning an optional or a, what is it called in other languages? A maybe, a Haskell maybe, or OCaml or Rust optional. Like maybe you elide that so the representation of the data is that type or nil. Stuff like that, optimizations like that are planned and of interest. A big thing with writing Coalton now is that like you're writing it in normal Common Lisp files in this thing called Coalton top level, and the editor support is not great. Imagine you have all of the types available. Why don't we have in Slime a way to show the types? Actually, Eiichiro Fukumachi, who's here, wrote a demo of how we can actually show, in the Slime mini buffer, or the whatever it's called at the bottom where it shows the arguments. With this little mode addition he made, it'll also show like the data type that's expected for each of those things. It's a really cool demo. You can maybe ask him to show it if he has it available with them. So, but to actually like ramp that up and make this more first class, I think is a big thing. We also approached using LSP. We tried it. It's, I wouldn't say done, but it's an experiment that's in the repository. We just don't have a complete story for editor support. And lastly, we did build a dedicated ASDF component, so you can write Coalton and have a Coalton file, and you don't have to write this Coalton top level thing or anything like that. You just have a dedicated file type. It still goes through the normal Lisp compilation process. It just is a little bit of syntactic sugar. That has not been formally adopted. We're interested in doing it because it's a nice way to write Coalton, I think, but that also requires better editor support. I think, above all, it's worth noting that Coalton has and always has followed the priority of production use. Like I am using, my previous employer is using Coalton for like real actual applications. So the design decisions that we make and so on are not based off of some theoretical concern. It's based off of what we need to do to get the job done. I also try not to, yes, I post Coalton on like Twitter and stuff from time to time, but we're not optimizing like cool websites and great tutorials. I'm not trying to optimize for getting the most number of people to write Coalton like many programming languages are. Again, I want to use Coalton to get a job done. And if that means there's only going to be 5 Coalton programmers in the world, so be it, as long as it gets the job done. If you're interested in Discord, there's a Coalton Discord. You can find that on the Coalton GitHub if you want. A lot of people have contributed to Coalton. Some open source contributors, some did internships with me at my former current employer. Some people work with me or have worked with me and contributed to Coalton. There's a good number of people who worked on Coalton or sponsored Coalton in some way, and so all of these people I have to thank for some contribution to Coalton. That's all I got. A couple little things. Like I said, the Discord link is there if you want that. The website, which basically has nothing on it except for the language reference or the standard library reference. You can look at that. My email is there. The job inquiries can also be sent there if you want to send resumes. And the code from this talk you can go find in my Lisp random repository on GitHub, ELS 2025. That's it. Thank you, everybody.
Okay. Thanks. I have 2 questions.
Yes.
First one, I may have missed it, but how can you optimize anything in the presence of a call to Lisp, which, if I understood correctly, has the ability to execute any arbitrary Lisp code, returning anything unpredictable at one time?
I did not talk about this, but I can talk about it briefly. So here's an example where like I said, I'm making a new Coalton data type for keywords. You have to promise that, so what is being sent in is going to be type checked already. So for example, here in this example where we're calling intern, I've declared this function as taking a string to a symbol. So it will verify that string, that the right data is being passed in. There is one promise you have to make, which is the output data type of this Lisp code. And here I'm stating it will be a symbol. Now, when we code gen this Lisp code, we are telling the compiler, turn on all the type checks, go back to normal sort of Lisp land. So there's no guarantee that there won't be type errors in there. You can make type errors the same as in Lisp. But kind of like the Rust unsafe keyword, at least it's like in a bounding box within the code. So short answer, no real guarantees. You have to tell the compiler, and the compiler will enable type checks again.
Yeah, but then if you enable type checks, you're actually not optimizing anything, right? In terms time-wise.
If you're not, say that again?
If you turn on the all the type checking in the Lisp layer,
yes,
the code will actually takes more time to
Yes,
execute.
yes. So in the standard library, for example, when we do floating point multiplication, we call into Lisp and then like turn type checks off again. So at some point we have to call the Common Lisp multiplication function for single floats, right? Somewhere in the code, we either specially code gen it or we define Coalton times as CL times. We do the latter. We define Coalton times as CL times. In there, we write a Common Lisp declaration saying turn off type checks again, because we know, like the code we verified, I mean, it's calling multiplication, right? There's not a lot to verify. So we verify things are correct there, and therefore the code that's generated will get caught in the whole SBCL optimization stuff, I would say.
Okay. Second question about monomorphization.
Yes.
Do you like generate new versions of every function and memorize them globally in order to reuse them, or do you like optimize a single function call, like a new tree of inline stuff, or?
Yep, yeah, great question. So we memoize them within the compilation unit. It's actually a big thing that we haven't done yet, where if you call monomorphize in different compilation units, but at the end of the day, they're sort of monomorphizing down the tree to the same functions, like multiplication or something like that, it's generating a completely new function. So that's wasteful, and that's something that should be redone. Monomorphization will monomorphize outside of the compilation unit, but that does mean kind of like with inlining, means the source code needs to exist, or some representation of it needs to exist.
Okay, so question 2.5, and I will stop there.
Yeah.
If you're creating new instances of the functions globally,
yes.
Have you ever think about for generating the source code for the monomorphized functions, so that the subsequent execution of the same application would benefit from that already?
Say that again. So have I thought about generating the source code? So are you saying so I don't have to re-monomorphize again?
Yeah.
Yes, so this is similar in spirit to like whether we cache them or not, like later on. They are generated as a part, like the definitions will come out of a macro expansion. They will be like in the FASL file with like a mangled name. But again, we haven't like done the work where later on we could refer back to that. I think that'd be a fantastic kind of little project that would. You're not going to notice many differences in like speed. It's going to be a lot more resourceful, I think. Yeah, those are fantastic ideas.
Hi, so suppose I had some piece of code that I wanted to write or rewrite in Coalton.
Yep.
And suppose also that for performance reasons I wanted to make it heavily parallelizable.
Yes.
How well does Coalton play with something like L-parallel?
Yeah, great question. So all Coalton functions, unless they are generic, meaning unless they take type variables, are just Common Lisp functions. Again, I didn't show an example here, but there are two ways to call into Coalton. You either wrap the Coalton, you're writing a bunch of Lisp code and you want to inject some Coalton into it. You can either use the special, that's kind of like a special form, quote unquote special form, Coalton, right? Open paren Coalton, write your Coalton code, and it'll work. Or if you know the function is already monomorphic, meaning it doesn't take any type class variables or dictionaries or whatever, you can just call it as a Common Lisp function. All the Coalton functions get translated into Common Lisp functions. The only trickery is when there are generic functions involved, and that's where you can't do it such directly. We do use L-parallel with Coalton. So calling Coalton code with L-parallel, yeah, no big deal. No big deal, asterisk, parallelization, broadly speaking, is difficult, and all that caveat, those caveats aside, calling Coalton within Lisp or vice versa is very, very easy. Likewise, using just any library. So like we're not going to rewrite everything into Coalton. There's no chance. We want to use Coalton libraries and so our Common Lisp libraries within Coalton. So that's why that Lisp form is there. Yep.
Okay, yeah, thanks for this great presentation. So I have a more general question. So
Yes.
you mentioned this thing about building mission critical applications. So safety is a
Yes.
really very important concern. How would you see this concerning verifications? I mean, you use the type information there. Is this also, so is verification in itself of the system, is this also something that is interesting in these domains that you're using Coalton, and can this be somehow supported by Coalton maybe?
Yeah, so I don't have a great answer. So the short answer is we're not doing anything beyond the verification that is done as a part of type checking. We don't produce any like certificate or anything like that to say this is true and correct. And with these Lisp forms embedded, there's no way to sort of prove that. You have to make a declaration that something is true. One thing we have been interested in is, because Coalton itself is like a giant Common Lisp program, we have like you as the programmer. I don't recommend you do this, but you as the programmer have access to everything that Coalton stores. So even though Coalton might use this stuff for monomorphization, you might want to use it for some sort of verification, or maybe you want to do some meta programming on the functions you defined, and you want to use the type information in order to do that meta programming. Or maybe something like along the lines of actual verification. We haven't done something like, I know Haskell and Quick Check aren't really what you're saying with verification, but we have experimented very briefly with the idea of using this. Beyond that, like into formal verification, I haven't thought too much about it myself, but it is an interesting avenue, I think.
The internet has several questions. The first one is, what kind of Lisp type does define type, the Coalton one, compile into? Does it even compile into the standard def type or something else?
Great question. So there's a document in the Coalton repository that describes the Coalton Lisp interop, because you need to know how something is going to be compiled if you're going to use it within Lisp. The answer is Coalton by default makes no promises what it's going to define. At minimum, it does promise that there will be something you can check with type P, but whether it compiles things into structs or classes or eliminates the structure class entirely and maybe makes a data structure, like for example, if you have like a wrapper structure you make, like that Fourier transform, where I made that finite field arithmetic here. I'm defining a new type finite field, and it has a constructor function f, meaning you call f on a UFix, and you get one of these finite field elements. In default development mode Coalton, that's going to define a new class with one slot, which has your UFix. However, because I wrote repr transparent, repr gives you, the programmer, a little bit control over what the representation of the data type is. And so what repr transparent says is, regardless of compilation mode, I want to guarantee f does not exist at runtime. So f will actually act as identity. It'll all be type checked because it's all statically type checked. So the answer is it depends. By default, there are no guarantees, but Coalton gives you a few options to provide that guarantee. And then there's a document in the repository that describes all of that.
Yeah, okay, so I saw in the beginning you said there's stuff about stack allocation and the memory allocation being more efficient. So I was wondering if that uses the SBCL support for stack allocation, or whether you manage that. I don't know if you know off the top of your head.
So,
is it managed yourself with memory?
No. We're not like managing the stack ourselves. This would be like with SBCL on dynamic extent and so on. We are doing the like escape analysis to see if we can declare it as DX, but no, we're not doing that management ourselves,
Okay,
at least not at this point.
And then my other question would be, since I've been working on the stack allocation support in SBCL for a few years, are there any points where you like declared something dynamic extent and then it just didn't? Because I was just curious, as a big user of dynamic extent and escape analysis, are there points where you just feel like the compiler isn't giving you the support? Because this would be an area where I would just create my own stack, stack management
we've
stuff.
been so there's a lot of work we've wanted to do with stack allocation. I don't think we've gotten into the real like meat of it yet. We've taken some cases where it's very obvious we're stack allocating, such as we're doing a pattern match on a data structure, like on a tuple, for example. We're pattern matching on a tuple and then immediately destructuring it. And we're able to detect certain cases like that to just stack allocate the tuple. I don't think we've gotten into the thick of it enough for me to start getting too much into the complications of it. I'm interested in how we could do stack allocation manually. I just don't know enough about how we would do it.
Okay. Is there any friction with interactive views and redav systems?
Yeah, good question. So by default in development mode, everything is defined as like classes, meaning like all these data types, for example, all defined as classes, and so on. So generally, we try to make it very redefinition friendly. Now, the natural question pops up, well, what if I redefine something and I change its type, but all the callers don't know about that, and so on? All that stuff will break, as would be the case in normal Common Lisp. If you recompile a function, you didn't update the call sites, those will also break. Right now, we have an active project happening where if you recompile something, we will try to record where those uses were and check if the new type of the function you're defining matches the call sites. Instead of erroring, we'll give you like a checklist to say, hey, here are the things that you just broke by recompiling this. Go fix them. In general, the experience is surprisingly good. The only trouble is like in Slime when you do like Control-C, it's like recompiling the whole compilation unit as opposed to an individual function. Because you do this Coalton top level thing, you write everything in Coalton top level, so Slime is just gonna redo everything. That's why we wanna have a dedicated file type so we can kind of control in a little more fine grain. So I think there's more work to do there, but it's surprisingly not bad. It's not 100% Common Lisp level, but 80%, I would say. All the normal workflow is what you do. It's just there was a couple little thorny areas, I would say. But on the whole, it's pretty good. Same thing with inlining. We do have, I didn't talk about the speculative, the heuristic inliner. We'll make decisions on like, is this code like small? And if it is, why don't we just inline it? And especially if we monomorphize and we see the code we're inlining is on double floats, well then we know we can unbox and do all of this. The same sort of issue pops up because if you inline something and you recompile, you could get those same issues. So yeah, there's a little bit of friction, but it's surprisingly not too bad, and there's more work to be done to make it better.
How well does Coalton work?
Who's taught? Oh, there.
How well does Coalton work with the Common Lisp macro system, using macros from Coalton, defining them for Coalton, that kind of thing?
Yep, great question. So if you define a normal Common Lisp macro, it will get expanded by Coalton. Now, I'm sure Common Lisp experts in here will find probably a way that breaks because macro expansion and the standard and what it dictates are kind of subtle, and making our own macro expanders, maybe not the smartest thing to do. But we do make sure that if we define a macro in Common Lisp, it will be expanded in Coalton. So we do this all the time. We don't attempt at any point, and we have zero interest in attempting to make a type-safe S expression data type. I think this is a red herring. I think it's a waste of time. I don't personally care about this. Just write your macros in Common Lisp. It's great at munging S expressions. You can munge together Coalton code if you want, and the Coalton compiler will macro expand it. So.
You have access to the Coalton information.
What did you say?
You have access to this?
Yeah, I mean, you have access to, the whole Coalton.
Can use that.
Yeah, of course, yeah. If you want.
That's what it should do.
Yes, absolutely, yeah. Well, so we've started to make an API, like a public API to the Coalton internals. It's not super formalized and whatever, but yeah, the whole type database and everything would be accessible to you when you're writing the macro, definitely, yeah.
Sorry, we're out of time, so last question, and it should be short.
Sorry. So we were just talking about how standard library development has been sort of like ad hoc.
Yes.
And I'm curious, like moving forward, like when you keep saying we, like who do we think of in terms of like the leadership team at Coalton, and also like how can we plan for it in terms of like it not being ad hoc? So like what does the 1.0 release look like?
Yeah, okay, this is another common question that we get online, like when is 1.0? When's that gonna happen? I am reticent to do any planning around it. We did write a big plan, like a project plan. What is the path to 1.0? What are all the features we need? I was originally I told myself the 1.0 is when I publish a paper about it, basically. Like when I publish a paper to ELS one year that says this is the definition of Coalton or something, that is when the 1.0 will be. I would say it will be a collaborative effort for as long as it is. So if people want to participate in working on Coalton, and there needs to now be some sort of governance structure that isn't just like Robert Smith and the people he manages, and it's going to be beyond that, then I think we're open to things a little bit. But right now, there's no like concrete plan, and like I said, there's a couple little pathways to 1.0, and you know, somebody, for example, some open source contributor wrote this whole design for the collections of the standard library. This phenomenal design. And I think if it's just a good idea, we'll adopt it. So it's a little old school in that way, but I think that's all I can say about that.
We're out of time. I see there are many people who want to still ask questions. I invite them to ask questions.
I'll be around.
Exactly.
So yeah, find me and happy to talk about it.
Thank you very much, Robert.
Yeah, thank you, everybody.